Welcome to the Chapter 8 lecture of Environmental Geography on Unstable Land. I am Nathan Bowden, your lecturer. In this chapter, you will learn how driving and resisting forces control slope stability, what factors initiate slope failure, including weather, earthquakes, and slope steepening, the characteristics of the different types of mass movements, including falls, slides, flows, and creep, what land subsidence is and how people's activities can cause it, how people attempt to protect property against unstable land and help prevent slope failure, and how science and engineering help guide land use decisions and help mitigate the impact of unstable land. Here are some few facts about slope stability. The resisting force is the force that opposes gravity and works in maintaining slope stability. If a slope becomes unstable, this is due to the driving forces being greater than the resisting forces. And the driving forces, of course, is gravity. The horizontal surface, gravity's entire force, is directed on the surface. However, in an inclined surface, gravity's force has two components. The first component, the GP, acts perpendicular to the slope, and the other component, the GS, acts parallel to the slope. If the resistance to the gravity's downslope pull is insufficient, the bedrock becomes unstable. In this figure, you see these two opposing forces. In A, you see a gentle slope in which the GP, the gravity perpendicular to the slope, is pulling object against the slope surface. The GS is the parallel force on the slope, pulling the object down and along the slope surface. In B, you see that the slope has steepened, and while the GP, the perpendicular component that's holding it to the surface, it has diminished, and the GS, the slope pull, has increased. And in this, on this B side, on the right-hand side, the chance of the slope failing is great. Resisting gravity, the existence of slope is the proof that forces do resist gravity. Some rocks, they have an internal strength that resists the gravity. It's either broken or weathered, then the gravity makes the loose fragments fall. Forces resisting gravity and loose materials are friction and cohesion. So friction in these loose materials is the resistance to movement. And cohesion is the force of attraction between certain grains of material. And this can vary with the material and also the amount of moisture that is present. Safety factors when assessing slope stability is the ratio of the resisting force to the driving force. So if the ratio is slightly greater than 1, the slope is close to being unstable. If the ratio is significantly greater than 1, the slope is to be said to be stable. And again, this depends upon the material strength, the density, volume, and slope steepness. So here you have in this picture two different types of bedrock. On the top is a block of sliding bedrock, and underneath that is the stationary bedrock. In between these two bedrocks, there's a little bit of space which has frictional forces that try to keep it in place. However, gravity also tries to pull it down the slope, the GS that is. Solid materials have a high internal strength and therefore form very stable slopes. Contact between the boundaries between different rock types is a weak zone. So if you have, let's say, a sandstone and another type of stone, then those two, the boundary between those two, as shown in the previous figure, created a weak zone. Tilted contacts also create weak zones for layers to break free. Faults and fractures are also weak zones. Slopes with very loose or unconsolidated material is also a very weak zone. The angle of repose, or the maximum slope, depends on the size and angularity of the grains. Slope steepness is the most important single factor in determining slope stability. As the slope gets steeper, the slope parallel driving force of gravity increases, so the GS increases. On a shallow incline, so a not steep incline, friction may prevent failure. If that is, of course, if the downslope pull of gravity is much less than the frictional resistance. So, if it's steeper, the downslope component of gravity is much larger than the friction, which would keep it in place. In this picture, you see two different types of stone, the sandstone and the shale being the gray, and the sandstone the tan color. This boundary between these two different types created a weak zone, and with certain weather conditions come about, it can easily let go and break. Water content and vegetation have a very big impact on slope failure. Water content increases the heaviness of the material, so this increase in weight will increase also the downslope component of the gravity, so the GS. It also decreases the internal resisting force by filling the pores in between the different zones. So this increases the pore pressure and decreases the internal strength of the material itself. Vegetation, however, has the opposite effect. Vegetation strengthens unconsolidated slope materials. The plants also work as pumps which remove the water from the ground, which in turn decreases the driving force and increases the resisting force. There are different types of unstable land, and slope failures show how quickly the material moves down the slope, the type of earth material involved, and the type of movement. Falls are the fastest mass movement, which is characterized by the tumbling and the rolling of materials down a steep slope or cliff. Specifically, these are rocks, which collect at the base of a cliff or a steep slope. A slide is also a sloping surface, and it can be either slow or rapid, and this is more common on surfaces that have been denuded. In other words, they have either trees have been removed or the grass has been removed. And in slides, you have less rock, or it's not only rock, it's also soil. And then there's the translational slide, which is a 2D planar surface. Here's a figure showing all four types, including the two types we already spoke of, and also two types we'll be speaking of soon. In the top, you see the fall, which is, like I mentioned, very quick. And as you see, it's on the very far right-hand side, so it's very quick, and involves debris and rock. The slide can go anywhere along the slow-fast continuum, but it also includes soil, debris, and rock. A slump we will talk about soon. It's similar to a slide, only on a less steep surface. And lastly, flows and creeps. These are normally in not very steep surfaces, and again, we'll talk about those in a moment. Transitional slide, as you see here, is normally along a slope failure. In this instance, it was you see a picture on the left-hand side, which was the largest landslide in the United States, 1925 in Wyoming. It was a translational slide. The slope failed along a weak and planar sedimentary layer, which is on top of the Amsdale shale layer. A rotational slide, and this one is a rotational slide in Japan. These are normally around serpentine or curved surfaces at the base, and in which the separate blocks on the slide material develop. Flows and creeps, on the other hand, and a flow is when a material begins to act more like a liquid and can move at a very high speed, and this always includes a lot of water. This debris is extremely mobile. It's actually a mix of debris, water, and of course a little bit of air, and these are also known as mud flows, which are a wet slurry of soil and a clay. Creeps are very slow, and this comes about by the fluctuation in temperature, freezing and thawing each year. Here is a figure of a creeping slope. One of the evidences you see on the bottom right-hand side of a creeping slope is the curvature of the base of the trunk. So the soil is slowly moving, and the roots of the tree have nestled deep into the soil, and it slowly brings the tree along with it. The roots stay where they were under normal conditions, and the base of the tree bends. Subsidence is a mass movement of land. They can be gradual or a sudden collapse. Regional subsidence is caused by compaction of underlying porous material. That's to say, the withdrawal of fluids, so the pumping out of water, underground water. It can also be karst-related subsidence, so a sinkhole, which is a underground cavern caused by dissolving rock, such as limestone. Karst landscapes have lots of sinkholes and caves, as well as streams, underground streams, suddenly appear. And there's also mining-related subsidence caused to mining activity. Here we see the formation of a karstland. So we have underground water filling caves and passages, and as the rivers above ground go through, it seeps into these large caves. These caves can then dry out or erode even further to the surface. And on the upper left-hand side, you see a sinkhole because the cave or passage developed close to the surface, and the surface collapsed. Causes of land failure include the weather, earthquakes, wildfires, slope steepening, and El Nino or La Nina, the change of the seasonal patterns of wetness and rain. And of course, people's activities. People develop things on slopes, and they are evident to subsidence. Here we see along the California coastline a landslide in La Conchita in 1995 and 2005, which devastated the city. People have a significant influence on slopes stability. In a negative way, they can construct facilities such as houses, which add weight to the slope and therefore increase the driving force down the slope. They can excavate terraces and pave roads, which may steepen the slope and also interrupts the drainage pattern of the water, which means there's more precipitation, more erosion, more saturation, and therefore an increase of the driving force, as mentioned in one of the first few slides, due to the increase of weight of the soil and filling the pores. The contact between the soil and the rocks has decreased. Septic systems, lawn sprinklers, and leaking water pipes can also increase the amount of water that infiltrates the hillside, and of course also increases the driving force. And lastly, of course, clearing the trees and the brush and other vegetation which holds the loose aggregate together will also decrease the resisting forces to gravity. Living with unstable land, first you should assess slope hazards. So using aerial and field surveys, if it's an undeveloped land, you look for scars in the landscape or sharp banks or tilted trees, which shows a creep. And in a developed area, of course, you'll see cracked sideways, fences, roads, and foundations of houses nearby. Landslide hazard maps can be developed to show where landslides are most likely to occur. And a landslide susceptibility map, which should show relationships among bedrock geology, such as previous landslides and slope steepness. And you must act, of course, on this hazard information. And here you see a few different of these possible geologic maps on either glacial deposits, you see on the top upper left hand, and also on landslides, and B from previous landslides. These two you can put together and develop a landslide hazard map, where the probability of landslide in the red zone is quite high, more than 10%, because you see this overlaps with a limestone, which means limestone can create a karstic environment, and also that previous landslides had happened there. So those two factors together increase the probability of a landslide happening and increasing the hazard. On the positive side, humans have an impact to slopes, and so you can engineer a stronger slope. You can do this by buttressing. There are many methods of buttressing, either making concrete retaining wall with using steel plates bolted together, or you can use a wall of steel or concrete piles along the base of the slope. Surface pins, are also called anchor bolts or soil nails, can be bolted into a surface to hold specifically two different types of rocks together. It increases the contact between the two areas. And another way is using nets of strong wet mesh. This will help hold small loose material in much the same way that grass or trees would do. You can also do check dams. A check dam is a kind of dam, but on land, that you can build along a slope. It partially blocks the drainages, so it decreases the flow velocity. And also it acts as capturing the heavier materials, such as boulders, so that they don't fall as far. And you can also, in places of high probability, real-time electronic landslide monitoring. Dewatering a slope is another way of increasing or decreasing the chance of a landslide. Here you see a solution where you have an initial water table, which is the top line, and a well is drilled much further than the water table, and to pump this water out, and this will increase the resisting force along that slope on the right-hand side of the figure, and therefore help prevent mass movements, such as a mudslide, which you saw in the one slide in California. Here is a picture of soil nailing, which you have a mat, and then steel rods are injected into the slope. There are a couple of ways to deal with subsidence. If it's a regional subsidence, this is normally due to overpumping of the groundwater. So you should strictly regulate the withdrawal of the groundwater and check to make sure there's been no illegal pumping of the groundwater. Encourage water conservation, so using just less water, everyone using less water, and switch to surface water supplies. And for some examples, that means importing water from a very long distance. You can slow subsidence, such as using imported surface water, by making reservoirs and retention ponds for stormwater runoff, and injecting injection wells to activate or recharge the aquifer. So in summary, slope stability is approximately defined as the interaction of the driving force, which is gravity, versus the resisting force, such as friction and cohesion. The changes in slope steepness, material character, water content, and vegetation cover changes can lead to unstable land. When land fails, it can cause downslope, subsidence, or collapse. There are different types of mass movement. These include falls, slides, and flows. A gradual mass movement is creep and subsidence. Karst is a special type of unstable land, which is due to dissolution of rocks, such as limestone, and withdrawal of fluids, especially water, from the subsurface leads to regional subsidence. Both natural processes and human activities initiate surface land movements, and living more safely on unstable land first requires delineating and assessing hazardous areas, such as by mapping and engineering approaches to help stabilize that land. Real-time monitoring and warning systems can help in areas that are especially prone to land failure. And how people use their understanding of unstable land, where it is and what causes it, is the biggest factor in mitigating these hazards. And lastly, land use decisions are a critical part of living more safely with unstable land. Thank you for your attention on this Chapter 8 of Environmental Geography.